So when you launch, I hope this is visible to everyone. So when you launch NengoGUI, there's a default network comes into picture here, which we do not need for this tutorial. We'll just get rid of it. Okay. So the idea behind spiking networks is that okay. So there are a number of ways to build deep spiking networks. And one of the ways is to go through ANN to SNN conversion, which has been shown in lots of work to be fetching a really good performance in deep spiking networks. So when going with the ANN to SNN conversion paradigm, we train a model, we train a traditional model with TensorFlow or any backend which we need to, and then we transfer those weights into an equivalent spiking network. So the idea is that the neurons in the spiking neurons in the spiking network, they are supposed to like represent the numbers, represent the real values through their spiking activity. So here I'm going to show you like how we can use Nengo to represent a real value. So going with it, let's start. Okay, so you definitely need to import a Nengo, and you need to create a model with you need to create a network object using Nengo.network. You need to name it model, because if you name it something different, it starts complaining. It says, I need the name with the model here. So be careful of that. Okay. So the way you create a Nengo network is like you define an ensemble of neurons, which is within the scope of model. So you can do this way. And in this ensemble of, yes,
we're still seeing the same fixed screen. Starts at the top with deploying SNN on LowE. Your screen hasn't changed.
Okay. Is the screen visible now?
Looks better screen now. I think it's updated now.
Okay, great, thank you. So oh, hi, hello Terry, thanks for being here.
Sorry, I'm late.
No worries, thank you for being here. Anyway, so I was just beginning here with the NengoGUI here. So I was saying that in this NengoGUI tool, you can create the Nengo networks as well as easily visualize them. So the way you do is like you need to first of all import the Nengo here, Nengo library, and then you need to create a model with Nengo.network. If you name it something different, which I was talking a bit earlier, then it's going to throw some error. It says it needs a network object named model. So that's what you name it. And the way you create a Nengo network is you define the network within the scope of model. And of course, a Nengo network is composed of ensembles of neurons, and then nodes and different other things. So we'll just start with an ensemble of neurons where the task of this network would be to represent a real value. So the way we do it is in this way, like we define Nengo.ensemble here, we create an object of it, and we denote the number of neurons that we want in this ensemble. So let's suppose we begin with just 10 number of neurons, and we set the dimensions to 1, which implies that it is going to represent a one-dimensional real value. So here you have, as soon as I complete the syntax, you will get a representation of an ensemble of neurons. These individual dots, they by no means represent individual neurons, but just a group of neurons. Okay, so we have an ensemble of neurons. Here it is, and let's feed some input value to it. So, that we can do by creating a node which does not have any neuron. It's just a programming construct to feed in some input values, or to receive some values from the ensembles. But here our use case is just feed some value. So let us feed a value of 1 to it. It's okay. This node is just outputting a value of 1, but it's still not feeding to an ensemble. To feed it to the ensemble, we need to create a connection from this stimulus input to the ensemble. So that we can do by simply calling nengo.connection on the stimulus input to ensemble. Great. For our purposes, we'll mention synapse equals to 0. The synapse equals to none here. I'll be talking about what the synapse does, but for the moment, we'll just mention synapse as none here. And there's a connection from input to the ensemble. Things are ready. So we'll see what value it represents, what value it feeds to this ensemble, and let us see what value this ensemble represents. You can also see the spikes generated by the neurons in this ensemble. So let's run it. Great. So it is feeding in the value 1 here, and the ensemble is also representing the value 1. For some reason, it's not spiking. Let me run it.
You might have the version of the GUI that has a broken spike display if you grab the latest version.
Oh,
there is one particular combination of a version of Python and a version of Nengo and a version of Nengo GUI that runs into that bug. To get around it, right-click on the ensembles and do the firing rate plot instead, or the firing pattern, sorry.
Yeah, that's a do it.
So, yeah. But yes, the latest version of everything, that bug is not there.
Okay, great. Thanks for helping that out. Okay, so I'm again deploying. Okay, I'm running the simulation here, and you can see if the neurons constantly firing, and it is representing the value 1 here. Okay, but the representation of the value of 1, which is being fed to this ensemble of neurons, is noisy. Can we smooth it out? Can we make it smoother? So that we do by mentioning the synapse. So that's exactly what I was talking about, that the synapse here is used to smooth out the incoming spikes or the spikes that you're receiving. So we can synapse here is it is implemented as a low pass filter, in which we need to mention a specific time constant. So that time constant you can mention as a value. We generally take the value of 0.005. Let's see if this has some effect on the represented value. No, it has worsened it, in fact. So I think the earlier synapse was larger than the synapse which I set. So let me set a higher synapse, 0.1, and see if it has some effect on it. Yep, it does have some effect, and you can see it gets smoother with increasing the value of synapse. Okay, but do we really need 10 neurons to represent a value? The idea, as I told you in n-to-n conversion method, is that we will have one spiking neuron corresponding to each rate neuron in a TensorFlow in a traditional model, and that spiking neuron is supposed to represent the activation value of the trained neurons in the traditional network. So we'll try to see how we can represent some real values with just one neuron, and let's see if we just keep it as such and we try to run the simulation, then no, for some reason it is not representing the value. It's still 0 here, and although the input is 1. Now, the reason is this neuron tuning curves, which shows that okay, so here there is just one neuron. So for an input of, for any positive input, this is the tuning curve which I'm focusing here. So for any positive input here from 0 to 1, this neuron is not outputting any outputting any spikes. So its firing rate is effectively 0 during this entire range. But for negative values, it is representing but it can represent negative values actually through its firing rate. So to overcome this, we can set proper values here. And let's set intercepts to 0. And let's see how it behaves. And there you go. It has somewhat started to represent a value closer to 1, and that's because just one neuron. Let's see how its tuning curve looks like. So yeah, so the intercept was set as 0. This intercept denotes that what should be the minimum input value beyond which the neuron starts spiking. So had I set an intercept of say -2, then the curve would have started from here. But here the intercept is set as 0, and I'm at a value of 1, it is firing at a maximum rate of 250 hertz. And that's what you're seeing as the output representing the value 1 here. Okay, so this is now, okay, so now I talked about representation of the values through spiking neurons, through individual spiking neurons. Now let's talk about another aspect which is very important for building deep spiking networks, and that's multiplication of weights. So in the connection weights. So that okay, for that we can do it very easily here. So we'll just create another ensemble. Let's go with 100 neurons this time. Okay, I'll just leave it to default. If you do not mention any encoders or intercepts, Nengo calculates it for you through some default method. There's still some issue here. Okay, like that. Create another ensemble of neurons. Okay. Now let's feed an value to it. Let's just feed the same value. I think I can, yeah, simply copy this. And let's also connect this ensemble 1 to ensemble 2. Let's set synapse for none for the time being, and we'll see its effect once again. Okay. Let's see the values which these ensembles represent. Okay, so I'm feeding a value of 1 from this input to this ensemble. This ensemble is representing a value of 1, which does a perfect job, somewhat perfect job. However, this ensemble here still it's noisy because of the noisier input from this ensemble to the next ensemble. It receives a noisier input, and so it represents a noisier output here. Okay, what can we do to smooth this? We can again mention here some synapse, which will help in smoothing it out. So let's go with 0.05. Let's see 0.005. Let's see if it, yeah, it's somewhat smoother. Okay. Now I want this ensemble of neurons to actually represent twice the value. So in a way, I want this connection to be a weighted connection of say, which simply multiplies the incoming weight by some real value, say 2. That we can do by mentioning here as a transform argument. Let's mention a transform of 2, and let's see how it behaves. Okay, it does something. So it feeds a value of 1. This ensemble is able to represent the value of 1 here. But when this ensemble is trying to represent a value of 2, which is 2 times, of course, the input 1, it fails. I'll get into the reason a bit later, but let's see, let's plot it from the range -1 to 2 and see how it behaves. Okay, so the actual value which it represents is actually 1.2 something. The reason is this ensemble's representational radius is still 1, which is the default radius. And the radius parameter here, okay, it shows, okay, so it determines the magnitude of the represented value. So the default radius is set to 1. Let's increase the radius to 2 and see how it behaves. And there you go. So for an input of 1 here to this ensemble, it represents the value of 1 here. And through this connection, through this weighted connection, it transforms that input to, scales that input to 2 times 1. And this ensemble is successfully able to represent the value 2. Great. So I have talked about 2 important aspects: representing a real value with a single neuron through proper choice of encoders, intercepts, and few other parameters are also there to be chosen, like max rate and stuff, which you can get more information when you go into the documentation of Nengo. And another aspect was, of course, multiplication of connection weights to the inputs. Great. Now, one more thing, by the way. So in the deep assonance in Nengo, we actually do a transform operation not on the ensemble connections, rather ensemble dot neurons. We just pick some values like the number of neurons we want, and then we do a transform operation. Okay. So time to now deploy, build a spiking network and see how we can deploy it on the LowE hardware. Okay, so now I need to go to my okay. Not exactly. Okay. Let's go here. So here we'll talk about building a spiking neural network in the NengoDL using the NengoDL library. Great. So as I told you in the very beginning, the motive is to go through, to build an SNN, the motive is to go through ANN to SNN conversion method. And for that very purpose, we will build a spiking, first of all, we'll build a traditional neural network with ReLU neurons. And NengoDL actually uses, I mean, like it is compatible with TensorFlow, so that's why we will be using TensorFlow to build our models. And the training or the inference in NengoDeal uses the TensorFlow backend. So after importing all these libraries, and I've written some utility functions just to aid us out here for building architectures. So we'll just import them. And for assistance, I'm also printing the versions in case folks are interested to reproduce this in their own environment. It's probably going to take some time. Okay, great, it's done. Now these are the environments. These are the versions of the library which I'm using. Great, and it's all standard, pretty standard. I'm just importing. I'm just loading that MNIST dataset. This is the exact dataset which we'll be using in our SMI projects, I believe. So yeah. So let's see what I'm getting a TensorFlow model here, and let's see what this model is. So in this model, we have an input layer, of course, of 28 cross 28 input size for MNIST, and we have this. It's not so special, but it's just a regular convolutional network, but it is important, which I'll tell you in the upcoming, in the next Jupyter notebook, which I'll be discussing. So there are 3 conv networks here, and they are strided, followed by a dense layer, and then followed by another dense layer, which is just simply an output layer. So we'll just call this TensorFlow to train this network. Let's do it in no time. Oh, maybe, okay, it's taking a bit of time. Shouldn't ideally.
I find the Zoom itself takes up so much processor that I find it actually impacts whenever I'm doing demos.
Yeah. Anyways, it has trained. Let's go and see how it works. Okay, so now I will convert this to a spiking neural network by calling this spatial function. Up till here, actually, it was all TensorFlow, so it's all fine. But from now onwards, the job of Nengo or NengoDeal starts. So I'll call this spatial converter function here to spatial converter class here to actually convert this TensorFlow model, which is now trained, into a spiking network. So we pass that trained TensorFlow model here itself. You can simply pass it here right after training, or maybe you can save the weights and then load it again and then pass it. Depends upon you. We also mentioned a proper we also mentioned this argument here, which is scale filing. Actually, I should have mentioned this here. Yeah, it's fine. It's the same. So we mentioned here the scale firing rates, which is in a way it helps us to alleviate the problem of dead neurons in the deeper layers. So what it does is it increases the firing rate of the neurons in the ensembles, and we swap those activation functions, which are ReLU functions, through by a spiking neuron. Here, I'll be experimenting with 2 neurons actually to show you how it behaves. For now, let's replace those traditional rate ReLU neurons by LowE spiking rectified linear neuron, which is actually a LowE version, LowE adaptable version of integrated fire neuron. And we also mentioned the synapse value, which I showed you in the previous Nengo tutorial. Previous Nengo demo, where this synapse value will be used to smooth out the spikes, the output spikes from the ensembles. So we'll just simply execute it. It should now we've got a converted model here, and let's see how it. Okay, let's just investigate what the layers here are in. here we have. So we get the ensembles by this syntax, and then you can see we have two spikes layer, which is an ensemble of neurons, which was of course here, and then we have this two conv layers. There's also a conv layer, by the way, and then we have a dense layer, and we have the number of neurons in them. So these are just an ensemble of neurons which I created in the which I showed you in the previous demo. And then we also have the connections from each of these ensembles to the next one. So we'll have a connection from input to the two spikes layer, and then we have a transform. This convolution transform is what doing the convolutional operation. And exactly this is the as I told you, this transform is used to multiply the weights to the input signals. Okay, they are more or less the same. Again, we have a transform. We have a connection from the conv 0 to conv 1 with a transform of this convolution operation, and we have a low pass filter there as well. You'll find this in each of these connections. Okay, yeah. This is I'm just printing the layers of the TensorFlow model. This will be used later here. Now to feed the values to the converted network, we have to get its input and output objects, or input and output layer objects, which we do by the syntax. So NDL model is actually your converted model, you can see here, and we just get the from the input, we pass the TensorFlow layers, the first layer, which is this input layer here, to get the input object of the converted network. Now let's suppose we want to also look into the spiking activity of some particular layer. So let's go with a convolutional layer. I think yeah, I'm plotting the I'll be plotting the spikes of this convolutional layer. So that's why here I'm using the index 2, and we'll choose some random neurons for which we want to plot the spiking activity. And that we so we have got the layer, we have got the neurons. The only remaining task is to probe that layer, which we will do by nengo.probe, and this is the output layer of the converted network. Great. Yeah, another important aspect of spiking network is that you need to represent your input values for some amount of time, such that the spiking activity occurs and then transfers throughout the network. So you need to present that input for some time steps, and that's what I'm doing here. I'll be representing the inputs for 30 time steps. So I've got my test images. I have flattened them out. That's required by Nengo. And then you tile those test images. So it's like test image, let's suppose that index 0 is now tiled 30 times to be shown to the network, and that's done for each of the test image. So now you can see there are 10,000 test images, and each of them is repeated 30 times, and it's just the flattened image vector, which is 28 cross 28, and it's 784. So now let's do some inference, but on the first 200 images. It's going to take a bit of time. It has no GPU. Let me see if I can get a GPU right now. Oh, I think it's already done actually. So it has now inferred. So let's see what the output looks like. The predicted output. So you will call this simulator again. Pass that converted model here, and you will feed that input images. It will do the prediction on those input images, and then you'll get your predicted data, which is the output classes. It has already done it. So let's see the shape of it. So as I said, I'll be inferring on the first 200 test images, and we have an output for each of the time step, starting starting from the 0th to the 30th time step. And there are 10 classes. It's all just prediction scores for each of the classes. That's the shape of this output matrix. Now, if I want to see the output of this network right at its 0th time step, then it's all some random value, but it's all just 1. So it has, it has not inferred any, it has not inferred any classes for the input images right at the 0th time step. But what about the last time step? At the last time step, we have all the inferred classes. So you can see the classes here for each of the 200 images. Now let's calculate its accuracy. It's pretty straightforward to follow. We have the argmax, which calculates which particular class has the highest logit score, and we just match it to equate it to the labels and take a mean of it, multiplied by 100 to get the percentage, and we have got 89% accuracy. That's sad. Why is that? So that the performance is very less. The reason is we are using LowE spiking rectified linear neuron, which is most suited to the LowE hardware, but we did not took proper measures for training with these neurons. We did not take proper measures while training to be inferred from these neurons. In LowE, the point is the spike amplitudes are fixed. It's going to be just 1. And the interspike intervals, that is the difference, that is the time difference between 2 spikes is going to be an integer amount. So an integer value. So say like 1 or 2 or 3 interspike time steps difference between 2 spikes, and so on and so forth. So that results into quantization of activation function, and a lot of information is lost here. So if we swap these LowE spiking, if we swap the ReLU functions, ReLU neurons with Nengo's spiking rectified linear neurons, we should have better results. Let's see. It's just doing the inference. How much time do I have? Yeah, I still have some time. Great. And there you go. We have 99% accuracy on the first 200 images. And this is the spiking activity of some random 256, I believe so. Yeah, of some random 256 neurons, which I chose from one of the conv, and you can see some random spiking activity here and there in those neurons. Great. So we now we have a NengoDL trained spiking network, but that is not suitable to be deployed on LowE. For that same reason, let's quickly go through this, like how we can deploy that on the LowE hardware. It's the same pretty standard. Let me just refresh it. So is that okay? Let me just restart. Yeah. Okay. Great. Here the usual importing of libraries. I'm actually running the same file. Okay. So in this file, I'll show you how to properly develop an architecture to be deployed, and a spiking network to be deployed on the LowE hardware. Again, the usual import of libraries and some utility functions. It will take some time. Okay, done. Here I've again loaded the TensorFlow, the MNest images from the TensorFlow library, and I have flattened those images, which is a requirement of the Nengo library. Just see, just flattens it out and keep. Of course, the number of images remains the same after flattening. Let's get the TensorFlow model. And it's the same model with input. There's a 2 spikes layer, then conv layer, and dense layers. Now we are having a 2 spikes layer here, which is, I told you it has a bit of a significance here. And that significance is that this particular 2 spikes layer actually runs off chip. So it doesn't run on the LowE, rather these 2 conv layers followed by this dense layer is what runs on the LowE chip. So the way I have built this architecture is that I have this 2 spikes conv layer, which is supposed to run off chip, and it is supposed to convert the input images to the spikes. So anything which you deploy on the LowE hardware should be given input as spikes. It doesn't work on the real values, the continuous real values, rather the spikes. So we have this special 2 spikes layer, which converts the input images to the spikes and then feeds those spikes to the next convolutional layers. This followed by this dense layer. And then we have this dense 1 layer, which is the last output layer, which is again run off chip just to collect the logit scores. Yeah. Okay. I'm just printing at the on-chip layers. We have these 3 layers which are supposed to be on-chip. This is exactly what you see here. And we have these TensorFlow layers. So nothing special up till now. Yeah. So now, as I showed you in the previous demo here, having a LowE spiking rectified linear neuron resulted into poor performance. So when the model was trained on the ReLU neurons. So this time what we do is we instead, this is a raw model. I mean to say it's not trained. It's a simple model, and then we are replacing those ReLU neurons by the LowE spiking rectified linear neurons before training. Actually, we mentioned the scale firing rates here 100. Once again, a value to help it better adapt to be converted to the spiking network when we deploy it on the LowE. And then we convert the model to a spiking. It's not necessarily okay. So it's not a spiking model here. Although I have mentioned a spiking rectified linear neuron here, internally it conveys the information to the NengoDL library that the NengoDL library still uses the ReLU neurons, but with an added information that okay, this is supposed to be deployed on the LowE hardware. So it adds some bells and whistles to adapt that network such that it caters for the quantization of the firing rates, which I was talking about earlier. So it has pretty much the same interface as TensorFlow. We'll again compile the model here within this simulator scope. We set the optimizer as Adam, pretty common, and then we use a sparse categorical cross entropy, and that's it. And then we fit the train images to the inputs, and in the outputs we just mentioned the training labels. We train it for 4 epochs, and then we save the model parameters. Just to keep in mind, it still uses the ReLU neuron internally to train the network. It might take some time. Okay, yeah, should be doable soon. I think I should have launched it to train and then explained it, but okay, doesn't take much time, so it should be done. Okay. So it's done. We will now be so as I told you that in the NengoDL spiking network, I had to represent, I had to show those images for certain time period. So here I'll be showing those images for 40 milliseconds of time. So here it just takes the values in this way. You mention it in seconds time. So it's 40 millisecond here, or 0.04 seconds, and that's the duration when each image will be represented. I'm again checking it on first 200 images, and let's see how it performs. So yeah, so I've got the model once again. The Nengo model, the converted Nengo model, and I have loaded the weights, and then I'm freezing the weights to be used. I mean, it needs the weights to be frozen so that it can be deployed in the NengoLoihi simulator. Here it is NengoDL simulator, and next we'll be deploying it on the NengoLoihi simulator here, as you can see. So before that, yes, we need a mechanism to feed those test images. So this is the interface that we use, a nengo.processes.present input. We feed in the test images to be represented, to be shown to the network, and then we have a presentation time, which is which has been shown here as 0.04, and there and we also mentioned that the first layer, the first conv layer, which is 2 spikes layer, is supposed to be done off chip. So that's what I mentioned here. I mentioned the 2 spikes layer to be run off chip. So I set the on chip value to false, so it doesn't run on the LowE chip. Now there is one important aspect when we deploy the spiking network on the LowE hardware. We need to break down those ensembles of neurons to the cores, to the LowE neurocores, and so that we do by using the block shape functionality exposed by NengoLoihi. So here we pass the number of neurons in a proper manner. Here it is simply rows cross columns of images, and here we have number of channels that should be mapped to one block of that should be mapped to one LowE core. So we need to do that for each of the conv layers that is running on chip. So if, as I've shown you that there are there are 2 conv layers which is running on chip, and there is a dense layer which is running on chip. So we need to divide, we need to distribute the ensemble of this conv layer to the neurocores. That's exactly what we do here for the first conv layer. This is done for the second conv layer, and then this is done for the dense layer, although it's not required here for the dense layer because the number of neurons is very less. It's just 100. For this dense layer, the number of neurons is just 100. So doesn't require, but anyways, we do that. We distribute those ensembles to the cores, and we simply run it on the NengoLoihi simulator. It still is not using hardware, rather it is using the simulator. But once you are able to run your network in the simulator successfully, then that means you can deploy that on the LowE hardware, and I mean, this gives you just like a first check to see if there is any issue or not. So let's just keep it running. We'll get the outputs in some time. I'm just testing for the first 200 images again. Yeah, so I'm running it for end test, which is 200 images times the presentation time, which is 0.04 0.04 seconds. You just get the data here. The predicted classes could be retrieved by using this data object here. Data attribute of this LowE sim object, and the standard method to just to match the LowE predictions to the test labels for calculating the accuracy. I just take a bit of time. It processes the images sequentially. So that's one of the things which we need to keep in mind on the LowE hardware. On the GPUs, you have batch processing, but on the LowE hardware, you need to process the images sequentially one by one. And you need to present those each image actually for some number of time steps. That's exactly what's happening here. So it's taking a bit of time. Okay. In the meantime, I'm trying to get. I'm trying to get the INRC LowE. Yeah, the LowE hardware on the INRC setup. So it's okay. Okay, there we go. So we have got the accuracy of 98.5% on the LowE simulator. So I'll just quickly, okay, I don't need this anymore now. This execution was done on the simulator actually, but this time we can do that on the hardware, and it's not going to take. Oh, yeah, it's not going to take much time. So what you can do is simply export this file as a Python file. From here, download as a Python file. You'll get it as a Python file, and then you can run it on the INRC VM if you have access to it. So, okay, so here is this Python file, the same file. I've just commented out the training part here, and we'll just do some inference. I have also transferred, copied the weights here on this on this VM. Now let's, okay, and one important aspect is here, which I wanted to show you, as this exactly, yeah. So here you saw I was using the target as the sim, which is the simulator part of the NengoLoihi. So it just emulates the hardware. There is no real hardware on my machine as of now. Whereas here I'm using NengoLoihi.simulator, and I'm leaving that as it is, which is effectively the same as mentioning here target equals to LowE. So this time it is supposed to run it on the hardware. So let's execute it on the hardware. I believe the number of images which I've set as 200 exactly. Presentation time is 0.03, which is a bit smaller for proper performance. So let's increase to 0.04, and that's it. You can execute this by this calling. Oh, okay, I need to, yeah, activate my proper environment for that, and that's it. It will execute in some time. It'll give us some results. I'll show you the execution here, and I'm all ready to take questions until it runs. That's it. That was my presentation. That was a tutorial actually. Thank you for coming in. I'll show you the execution in some time. But I'm ready to take questions in the meantime.